The blood specimens that will be used in this and all succeeding experiments are taken from an apparently normal, healthy donor. They'll be drawn from the marginal blood pool, generally from a fingertip. We're going to take that blood for direct microscopic examination, and for baseline readings, we're going to suspend it in a material called Lox solution. Lox solution is essentially a physiological saline, which is buffered for pH purposes, and has a few extra minerals added to support damaged or unhealthy cells. When we mix our challenge materials, such as an anesthetic or other things that we will look at, we will also suspend these materials in Lox solution. As we mix them together, keep in mind that the final concentration that will be examined is 1 part of challenge per 10 million parts of diluent, blood, and Lox solution. Within 30 to 60 seconds of adding the anesthetic to the blood mix, we notice that there's a very peculiar increase in fibrin. There are strange structures showing in the fibrin tangles and bundles. The erythrocytes have lost substantial density, and we notice that the PMN has shifted out of its typical blue-violet coloration and has a marked increase in its activity rate. The granules show white, which we associate with high rates of energy expenditure. As the anesthetic continues to have its effect, we see little or no indentation left in the morphology of the red cells. The white cell continues to whiten and increase in activity, and the bundles of fibrin continue to intensify. These changes are vastly different from those caused by the metals. This PMN has lost its integrity. It has lysed, and part of its cellular content is spilling out into the plasma. This happens with a number of the white blood cells. After about 45 minutes to 1 hour from initial exposure, we notice here that there are some peculiar changes now taking place that differ dramatically from those induced by the heavy metals. We notice that there is a modicum of form and function beginning to return to the white blood cells, and we notice that the fibrin bundles and tangles are beginning to resolve somewhat. We notice here in the background that the outlines of the red blood cells are beginning to become slightly more prominent. The nuclei of this PMN are beginning to form into a more normal morphology, and we see some organization returning to the granules of this cell. The volume of this lymphocyte is beginning to dramatically reduce and to assume a more normal proportion. In about 90 minutes, we notice that the erythrocytes are beginning to take on a more normal morphology. There's the return of a slight shimmer pattern, and here and there we can begin to see the dimple or indentation in the morphology of these cells. In the 60 to 90 minute time frame, we begin to see motility returning to the PMNs. They begin their migratory movement around among the red cells, and we still see the indentations and shimmer returning to some of the erythrocytes. At about the 2-hour mark, most of the red cells are beginning to look fairly normal. There is still a little aniso and poikilocytosis here, but the cells begin to look like the red cells that we started with. At about the 3-hour mark, most of the red cells seem to appear somewhat normal and again very much like the cells that we started with. Unlike the heavy metal changes, we notice that most of the changes induced by the anesthetics are reversible. Remember that these changes are transient or temporary. But what happens when we get into some of the forms of chemicals that are associated with the breakdown or corrosion of biorestoratives such as dental products? What happens when we add things like aluminum or mercury to these blood cells at very, very dilute concentrations? Let me show you the tragic changes that come to blood cells at 1 part per 10 million exposure rate. These changes will not reverse.